In this video, we're going to quickly go over a mathematical concept called projections that comes up often in the mathematics that we apply when we analyze high-dimensional data. So to understand projections, we're going to use the notation of linear algebra. We start with this cartoon that shows a point with the first big arrow. That is the point that's being projected to a space, which is represented by a line. And the dotted line is the projection of the point to the subspace. And you can think of it as the location where the shadow of the person standing on the space would fall. So here, we're going to use the notation y with a little arrow on top. That's what is used in most linear algebra textbooks. And we're going to think, in general, it's a point in n-dimensional space. So although all our cartoons are in 2 dimensions, you want to abstract away and think of it as being in any dimensional space. So for example, if you have a data set that has 100 points, that would be in n-dimensional space. And then we're going to use the notation L to represent the subspace to which we're projecting. In this case, that line that you see would be L, and those are all the points. They're in 2-dimensional space, but they're all the points that fall on that line, so it's a smaller subspace. So let's consider a very simple example. Here is a point y. It's in 2-dimensional space. We can represent it with a vector 2, 3. And what we're going to do first is define some terminology. So we say that 2, 3, you can think of it as the number 2 multiplied by the vector 1, 0, plus the number 3 multiplied by the vector 0, 1. And this seems overcomplicated, but it makes thinking about some of the mathematical techniques that we use easier later on. So here the terminology is that 2 and 3 are called the coordinates, and then the 2 vectors 1, 0 and 0, 1 are called the bases. So what you should see here is that any point in 2 dimensions, any point that you pick, can be written as two coordinates multiplied by these 2 bases. So here's a simple example that is that helps us understand what spaces and subspaces are. So here we have the red line. That is a subspace of 2-dimensional space. So 2-dimensional space are all the points in 2 dimensions, and then there's the points on the red line. So those points can be written mathematically as points that are satisfy a constant c multiplied by the vector 2, 1. So any point on that line will have that property. It could be written as c times and then the vector 2 minus 1. So that defines our subspace. So now the projection is the closest point on this red line L to the point y. That's what we call the projection. And we're going to see a couple of examples of projections applied in practice, so you can see why they're useful. But for now, we're going to focus on explaining what it is mathematically. So what we want to do is we're going to show a mathematical procedure that helps us find the projection of y onto this space. And we're going to write it as y hat. And what it comes down to is finding the c hat that satisfies this property, that's the closest point. So we are going to give a more complicated example here that is a little bit more general. Now y is in Rn space, meaning it's n-dimensional. And L is a specific subspace of all the points in n-dimensional space that are all the same. Right, so the way we would write it is like this. We would have v with an arrow on top. That's going to be the vector that defines the space. It's just many ones, all ones. And now L, the space of all the vectors that are all the same, that are constant, is basically the constant c times v. So members of this space would be 1, 1, 1, 1, 1, or 2, 2, 2, 2, 2, etc. So what we want to find is the c to find the projection of y onto this space. We want to find the c that minimizes the distance between c times v and y. So we have a notation that you see here. The answer to that is the projection of y onto L. So how do we find this c? So let's go back to the cartoon, that's the simple example. The general solution to this problem is using the fact that the difference between the original point and the projection, that would be y minus c hat v, multiplied, and this is matrix multiplication, it's called the dot product in linear algebra, times v is equal to 0. So the difference between the original point and the projection is, we say, orthogonal to the space. So once we write this equation out, we find there's the solution. We can solve this using the linear algebra that we've learned. And remember that here, x times y, in general, this dot is the matrix multiplication that we see here at the bottom. All right, so if we solve it for that first problem that we encountered, if we just do the math, we get that the answer for the c that minimizes the distance between the point and the space is the average of y. And that is what we get from this, that if you project a point in n dimensions to the space spanned by points that are all the same, is the average. So this is one way, one maybe convoluted way of defining or finding or motivating averages. Now in this case, we don't have to do all this linear algebra, because we can use calculus to find the c that minimizes this distance. And you can see, following the equations shown here, that you get the same answer. So let's start a slightly more complicated example, and it relates to regression. So if we are going to find the regression line that best fits the data, that could also be explained with projections. So here the subspace that we're projecting to is the space of all lines. So we have a point in n dimensions, that's our data, and we want to find the line that best fits that data. We can ask, what is the line in the subspace defined by all lines that you can see in this equation here that is closest to the data. So to do that, we will define two basis vectors. v0 here is just all ones, and v1 are our x's that we are performing the regression on. So if we do that and we solve using our linear algebra and the definition, the multidimensional definition of orthogonal projection, which is shown in this equation here, we get the same solution we obtained in a previous course on linear algebra for the line that best fits the data, which is basically comes down to estimating the coefficients beta using least squares. So this is an example. These are two examples of how projections, we have already in a way been using projections to solve real problems in data analysis. And when we learn more about singular value decomposition and principal component analysis, we're again going to be performing projections such as this.